Okay, quadratic models. So we've modeled some things with linear relationships. We can do the same with quadratics. So let's look at a word problem. The marketing department at Texas Instrument has found that when certain calculators are sold at a price of $P per unit, the number of calculators sold, X, is given by the demand equation. X is 26,000 minus 160P. It's supposed to say P. Okay. Find a model that expresses the revenue as a function of the price. Well, revenue is what you get when you multiply the quantity that you sell times the price. And so quantity we can abbreviate with X, I think, in our model. What do we say? Quantity, yep, is X, and price is P. And we were told that X is 26,000 minus 160P. So we can replace multiply by P, and then this is the revenue based on the price. B says, what is the domain of R? Well, the domain of R is depending a little bit, obviously, on X, the quantity, and on the price. So the quantity, which is our X, has to be larger than 0. So X has to be larger than or equal to 0. If that is true, then 26,000 minus 160P has to be larger than or equal to 0, because we know that X equals 26,000 minus 160P. So we can solve this. So 26,000 is greater than or equal to 160P divided by 160. So P would be less than or equal to, and it comes out as 162.5. So the domain would be between 0 and 162.50. What unit price should be used to maximize the revenue? Well, this ends up being in a quadratic, and if I multiply it out, you see that a little easier. So it's a negative 160p squared plus 26,000p. Well, quadratics have a vertex, and in this case, because the thing opens down, it's going to be a maximum. So the vertex would be at a negative b over 2a, which is a negative 26,000 divided by 2 times a negative 160, and that comes out as $81.25. If this price is charged, what is the maximum revenue? Well, revenue is equal to 160p squared plus 26,000 times p again. Okay. With the calculator, we can't do that in our head, and neither really could we do the previous one. It's $1,056,250. How many units are sold at that price, or at this price? Well, I started out by saying that revenue is the quantity times the price. So the quantity must be the revenue divided by the price. And we just calculated that. And that revenue at this price, so there's a decimal there, should give you the quantity. So that ends up being 13,000. And then F, graph R. So graphing this, you can write go to GeoGebra and graph it. That would probably be the easiest way to do that. Okay. Next word problem. The Golden Gate Bridge, suspension bridge, spans the entrance to San Francisco Bay. Its 746 foot tall towers are 4,200 feet apart. It's suspended from 2 huge cables more than 3 feet in diameter. The 90-foot wide roadway is 220 feet above the water. So there's the 220. From here to here is the 4,200 feet that they were talking about. And since we are 746 foot tall towers, but they equate to 220, that leaves 526 here and marked here. The cables are parabolic in shape, somewhat, and touch the road surface at the center of the bridge. So they touch right there. Find the height of the cable at a distance of 1,000 feet from the center. So if it's parabolic, then that means that this is some sort of an x squared. And since they put the vertex right at 0, 0, we actually know that this particular quadratic is an ax squared. It doesn't have anything else. And that should be enough to find the information, because, or to write the actual equation, because we know, for example, that this point has to be on that equation. So 526 equals a times 2100 squared. So a is whatever this equals. Don't multiply it out, just work with it for now, because ultimately we're really not interested in what a is. We want to work with this expression, and we need to evaluate this at 1,000 feet from the center. So plug in 1,000. Make sure you get a calculator. And if you do this, then y ends up being 119.3 feet approximately. Alright, next one. So here we are looking at what happens if we have a bunch of data. In this particular case, you see the data could be modeled by something like this. Well, that could be a quadratic. Maybe I need a little more symmetry, maybe I need to learn how to draw a little bit better, but you can see that these two scatter plots can be reasonably well modeled by a quadratic equation. So that's what we're going to do next. So let's say we have the following situation. We have a set of data that's collected like this, and it shows the crop yields y for various amounts x of fertilizer used. So x is the independent, so very nice for us. That's independent, and yield is dependent. And we are going to use a graphing utility to find the quadratic function of best fit. Well, how did we know it needed to be quadratic? If you look at the graph of the data, you can see that this looks to have a curve like this to it. Okay, so in this particular area, that could be a quadratic. Now I know it might be a cubic and wiggle and stuff, but locally this could be modeled with a quadratic, probably. And we're going to go ahead and use the internet to find that function. So where do I have my, there it is. Okay, this is the website that you're used to. Unfortunately, we've done linear regressions with this so far, or unfortunately, so far we've only done linear regressions. We need to do a quadratic. Well, there are different regressions up here. So that's the linear. That's a logarithmic. It's definitely not it. Exponential. Power could be it, but a power function is so power function would just be an ax squared, for example, since we're dealing with quadratics. It wouldn't have any other stuff behind it. So the power function may not capture exactly what we need. We're going to actually do this with a polynomial regression. And the polynomial allows you to set the degree that you want. And in this case, if we want a quadratic, we will want to use 2 as our degree. So we're going to enter the data. There it is. I cheated, obviously. I did this earlier. Here's all the data. Once it's in, you just tell it calculate, and it will spit out the equation that we need. And there it is. Negative 1.71 blah 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 times 10 to the negative second. Make sure you check this here, because it's not a negative 1. It's going to be a negative, or it's going to be negative 0.0, and then we'll round. And then here, this one is right, so that's 1.077, and this is 3.89. We don't have a times 10, so that's the equation. Okay, so we're going to use that equation, and that models this data fairly well. How well? Actually, I don't know, and I should probably check on that. So based on the website, we have yield equals a negative 0.0171 times the fertilizer squared plus 1.077 times the amount of fertilizer, and then the constant that we're adding is 3.894. So I'm curious, I forgot to check. Let's see, how well did this do? So we're looking at these errors over here. So that's 10 negative, that's actually a decimal. So that's small, not too bad, not too bad. So 3, 8, that's to the negative first, another 2. So we're pretty close. The predictions are pretty close to 3.89 is pretty close to 4. 20.1 is pretty close to 20. So that looks to be a reasonably good fit. Okay? Alright, back to this then. B. Use the function to determine the optimal amount. Well, again, it's quadratic. So optimum, negative b over 2a. In this case, a negative 1.077 divided by 2 times a negative 0.0171. Plug that in the calculator, should give you a positive, and that gives you 31.49 as the amount of fertilizer we're going to use. So that is pounds per 100 square feet. Okay, is that what they were asking me? Optimum amount of fertilizer, yes, and then C actually tells you what is the predicted crop yield for the optimal amount. So plug this in. This is your X, or in this case the fertilizer. Plug that in to the yield, and if you do this, you should get about 20.85 rounded. So 20.85 bushels is what our yield is predicted to be. Now that's pretty close here. We see 21 and 22. So 22 is the largest number that we saw. You can't always expect to get the largest possible. So this seems to be a reasonable estimate. Okay? Thank you.